Hello, everyone. For today's MICCAI RISE Journal Club session. Today we have a special guest. He's Pedro Bassi, a postdoctoral researcher at Johns Hopkins University. And today, Pedro is going to present his last paper that won the Best Paper Award at last MICCAI 2025. Pardon. Learning segmentation from radiology reports, a scalable path to multi-tumor detection. So without further ado, I hand over to Pedro. Thank you very much.
Thank you very much. So let me share my screen. Okay, so thank you very much for the presentation. Yes, my name is Pedro Bassi. I'm postdoc researcher at Johns Hopkins, Department of Computer Science. And I work closely with Professor Adam Yuyo and Professor Zhongwei Zhou. And here I will present about our paper, Learning Segmentation from Radiology Reports. Also, I would like in the beginning to thank my co-authors, Wenxin Li, Zhenan Chen, Jaden, Tianyu, Sergio, Andrea, Kang, Yang, Alan, and Zhongwei. Okay. Also, thank you for the MICCAI Society for the Best Paper Awards runner-up, and also thank for the RSNA Society because this paper just received the Certificate of Merit Awards as it was presented in, its abstract was presented in RSNA this week. Okay, so now let's start. I will start with a little bit of context because this is a work about tumor detection. And why is tumor detection important? Especially why is early tumor detection important? It's important because when tumors are detected early, the patient has a much higher chance of survival. So when tumors are detected early, often we have above 90% probability of the patient surviving the next 5 years. However, when tumors are detected late, this probability often drops below 20%. And that's because the tumor can become large. It can involve blood vessels, meaning it cannot be removed anymore by surgery. And because the tumor may have spread to multiple places in the body, which make prognosis much worse. So it's very important to detect tumors early. And each year, about 300 million CT scans are done all over the world. So this is a large number of scans that offer us a big opportunity for opportunistic or incidental tumor detection. What I mean is the CT scans are done for multiple reasons, but sometimes there can be a tumor in these patients, an early tumor, and it would be excellent if we can detect this tumor early and treat the patients. However, what's the problem? The problem is that tumors are often very difficult to see. So, for example, a study showed that radiologists often miss about half of early pancreatic tumors. And pancreatic tumors are extremely aggressive. So detecting them early is very important. However, AI can see things, subtle details in the image that humans cannot perceive easily. So other studies show that AI can detect pancreatic tumors even in non-contrast CT with sensitivity and specificity greater than 90%. So these are results much higher than what humans can achieve. And for this task of using AI to help radiologists detect tumors early, segmentation models are especially useful because they are the current state of the art with the best performance in detecting tumors. Also, they offer interpretability and more trustability because they will not only tell the radiologist there is a tumor, but they will show where the tumor is. So the radiologist can understand and verify the AI decision. So here is a successful story. This is still the context for our paper, not our paper itself. But this is another project at Johns Hopkins University where we created an AI to detect pancreatic tumors in CT scans. So we had a large reader study with about 30 radiologists, and in this reader study, we found that the radiologists could find early pancreatic tumors in only 33 to 44% of the cases. And these numbers matches other studies in the literature. However, our AI could detect these tumors, these small tumors smaller than 2 centimeters, with a much better sensitivity, above around 94%, also with a higher specificity. Oh, just one thing. If you have questions, please write them in the QA session, and I will answer them in the end of the presentation. Going back. So you see, this AI has the potential to help radiologists. It can detect many tumors that radiologists could not see. But what's the story behind this? So the behind the scene is that what makes this AI model, the segmentation model, so strong is the data set. So for this project, we created a very large data set. This was called the Felix project at Johns Hopkins University. In this project, more than 5,000 CT scans were annotated, meaning that radiologists went into the CT scans and annotated the pancreatic tumors per voxel in the 3D image. This took 5 radiologists for working for 5 years and $6 million in funding. So you see, this is an extremely creating the tumor segmentation masks is extremely time consuming and expensive and inaccessible to a large amount of research teams. Even for our team at Johns Hopkins, we had this big investment to create a strong AI model, which we trained on these data sets. But this is for the detection of one tumor type, pancreatic tumors, and we train it in one hospital. What if you want to detect all tumor types, 10 tumor types? And if you want to train on 10 hospitals, 100 hospitals, what do you do? This is not scalable. The amount of money and time that would be needed to create masks for all these tumor types is too much. This further shows you the problem. So here we have in gray the public tumor segmentation data sets. So you see that if you want to segment tumors in the liver, pancreas, and kidney in CT scans, the largest public data sets like Abdomen Atlas, PANTS, will give you around 1,000 tumor segmentation masks for each one of these tumor types. For other tumor types like colon, you can find at most around 200 tumor segmentation masks in the public domain in MSD. And for other tumors like adrenal glands, you can find only 50. And for tumors in the uterus, prostate, esophagus, spleen, bladder, and gallbladder, you find 0 public segmentation masks. So you see, this is a big problem. If you want to segment these tumors, you have no public mask to train from. You would need to hire a radiologist, create a lot of masks, spend a lot of time, because there's nothing in the public domain. And even if you want to segment tumors in the liver, pancreas, kidneys, also lungs, you have public masks, but the number is not super large. We all know that AI gets better when you have more data. And currently we have at most 1,000 something masks for each one of these tumor types. So you see that masks are the big bottleneck for tumor segmentation. We have no masks for many tumor types, and even for the types where we have masks, there are not too many. So in this project, we look to another type of supervision. We look to radiology reports. Radiology reports are texts that describe the findings in the CT scan or in other types of images like MRI or X-ray. So the reports will describe in words the tumors in the CT scans and other findings as well. And the big difference between CT scans and masks is that between reports and masks is that the creation of reports is part of the radiologist's everyday work. So whenever someone has a CT scan or an X-ray or MRI, the radiologist will write a report explaining the tumors and the findings in this image, but he will not do a segmentation mask. Segmentation masks are only created for research. That's why they are so few. So basically all X-rays, CT scans, MRIs in a hospital has a radiology reports. If you look at public data sets, we have here the Merlin data set from Stanford, just released a few months ago. And Merlin has 25,000 CT scans with radiology reports, no mask. And these reports includes all of these tumor types, even those that have no mask in the public domain. And 16,000 CT scans in these data sets have tumor reports. And if you look for a single hospital, here we have the UCSF hospital, we can find more than 100,000 CT scans with tumor reports in that hospital. So the picture is clear here in this plot. The datasets with reports are much larger and cover many more tumor types than the datasets with masks. Also, the reports are very useful. They contain very rich information. So when we think of reports, you can recall the captions that people use in computer vision. But the captions for natural images are nothing like the reports that we have in medical images, because a caption, usually taken from social media, may have nothing to do actually with the image. It will not always, usually it will not carefully describe what you see in the image, as shown in this Twitter post here as an example. However, the reports are different. The reports will carefully describe the important medical findings inside the medical image. It will describe the tumors. It will give you the tumor size. It will give you the tumor location, meaning which organ or even which parts of the organ the tumor is. It will give you the tumor attenuation, meaning is the tumor dark or bright? And it will tell you how many tumors exist. So we have this rich information, geometrical information. And the question is how to use this information to improve tumor segmentation. We do not want to simply go with the methodologies used for natural images, like, for example, pre-training with clipped and fine-tuning with masks, because these methodologies are created for the captions, which, as we show, are very different from reports. Reports have much more geometrical, rich information that we think we can extract and use more effectively. So now I present to you our methodology. Our new methodology is a training methodology that we call reports supervision. And this methodology trains tumor segmentation AI, tumor segmentation models to segment tumors that match the tumor descriptions inside radiology reports. And what I mean is it trains the tumor segmentation model to segment tumors that match reports in the number of tumors, in the size of each tumor, the location of each tumor, and the attenuation of each tumor. So how do we do this? First, we take all the reports and we use a large language model, a pre-trained frozen large language model, and we use it to read all the reports and extract the important tumor information. So it will extract the tumor location, diameter, number, and attenuation. We store all this information and we only run this large language model once. We don't train it, so it's not something much expensive computationally. Then, after extracting this information, we go to train the segmentation model. And this is where the main novelty of our work is, because here we have new loss functions. We have three new loss functions: the volume loss, the ball loss, and the attenuation loss. And these loss functions will teach the segmentation model to segment tumors, matching the tumor descriptions in the reports. So for example, if this segmentation model segments a tumor with 1 centimeter and the report says that this tumor has 2 centimeters, the loss function will penalize the model to make this tumor larger. Importantly, this methodology can be used, so you can train only with reports, only with CT scans and reports. So in this case, you are entirely substituting masks by reports. Or you can train with both masks and reports. So you can create a large data set where some CT scans have only masks, other CT scans have only reports. And then when you have a CT scan with reports, you use our loss functions. When you have a CT scan with masks, you use the standard segmentation losses like dice loss, cross-entropy loss. Another important thing is that reports are used only in training. Here, reports are our ground truth or labels for training. During inference, during testing, the segmentation model just takes the CT scan, segments the tumor. It does not read the reports. And finally, this is a training methodology. So it can train any architecture. In our experiments, we use it in the match forward. But if you create a new segmentation architecture, you can use it here. Just train it with our loss functions. And yeah, you can train your new architecture with reports. Okay, so now let me describe our new loss functions, which is the core of this work. The first one is the volume loss. The volume loss is a less strict loss function. So it's also a loss function that's easier to optimize. And this is important to achieve a good performance and a good convergence during training. What does this volume loss do? It will teach the segmentation model to segment tumors that match the tumor volume estimated from the reports. You know, reports usually do not have tumor volumes. Actually, I believe they never have the tumor volume. But the reports tell you the diameter of the tumors. So from the diameters, we can estimate volumes. If the report only gives one diameter, like the tumor has 3 centimeters, we can estimate the volume of this tumor as a sphere. If the report gives multiple diameters, then we can estimate the volume of the tumor as an ellipsoid, which is more precise. So what we do is for each organ that has tumors, according to the report, estimate the volume of all the tumors inside this organ, we sum them, and then we have the estimation of tumor volume from the reports. And then we need to estimate the tumor volume from the segmentation. So we apply this loss function as deep supervision, but we take the output of a layer in the decoder of our segmentation model, and then we apply a last layer to get tumor probabilities. And we have basically the segmentation output. So the probability of tumor in each voxel. Then inside these segmentation outputs, segmentation map, we need to find the organ that has tumors. So if the report says the spleen has tumors, we need to find the spleen. How to do this? We use simply a pre-saved organ segmentation mask. And here, we leverage the fact that there are many models already public, already pre-trained to segment organs, and they can do this with a pretty good performance. So the dice score for organ segmentation is usually much, much higher than dice scores for tumor segmentations. So for example, you can use total segmentator that can segment tens of organs and segment the spleen. And then you save the spleen segmentation mask and use it here to locate the spleen. So the organ segmentation mask is helping our loss function. Okay, so we will locate the organ that has tumors. And then everything outside this organ, our loss function will minimize. So it minimizes tumor segmentations, tumor probabilities outside the organ that has tumors. Then inside the organ that has tumors, we need to estimate the total tumor volume. This is basically like counting voxels. If you imagine the tumor segmentation outputs as a binary segmentation mask, you would need only to count the voxels. That's R1, the tumor voxels, and multiply by the volume of one voxel. Actually, the tumor segmentation outputs are probabilities, but we can just sum all the tumor probabilities inside the organ, multiply by the voxel volume, and then we have a rough estimate of the total segmented tumor volume inside this organ. And then we go to our loss function, and we have this curve here. And what this loss function will do is it will train the total segmented tumor volume to match the volume from the reports. So for example, here in this plot, we consider that the volume from the reports is 1,000 cubic millimeters. And then if the segmented tumor volume here in the x-axis is 1,000, the loss is 0. If the segmented tumor volume is 0, then we have a high loss and importantly, a very strong gradient. And this strong gradient is important to avoid false negatives. So it will strongly penalize the segmentation model if there is a tumor and it does not find any tumor. Then around 1,000, you can see here a flat region in our loss function. And that's something we want. That's a tolerance. What it means is if the segmentation model segments a tumor volume that's very close to the volume in the reports, we don't penalize the segmentation model at all because this volume from the reports is not perfect. The diameters in the reports are not perfect. If you ask two radiologists to measure one tumor, probably you'll get some difference between the measurements. And also the estimation of volume from diameters is not perfect. So that's why we have this margin. It's about 10% margin. If the segmented volume is about 10% difference, it's below 10% difference from the report volume, there is no penalization to the AI model. And then here, if the segmented volume is much larger than the volume from the reports, again, we penalize the AI model, but with gradients that are not as strong as here in the left side. The reason is that if you have very strong gradients here, we can penalize the AI too much and it will simply say there's no tumor anywhere. It makes everything 0. So we need some design of this loss function here. You can find the exact equations in the paper. Okay, now we go to our second loss function, which is the bow loss. The bow loss is more strict than the volume loss, and it's applied to the last layer of the segmenter. It's more strict because it will teach the segmentation model to segment tumors that match the reports in terms of tumor diameters, tumor locations, and the number of tumors. How do we do that? So again, first we locate in the outputs of the segmentation model where is the organ with tumors. So in this example, the tumor is in the spleen. So again, we use a spleen segmentation mask to locate the spleen. Again, everything outside the organ, the tumor probabilities there are minimized. So we do not, if the report says the tumor is in the spleen, we do not want to segment tumor outside the spleen. We have some tolerance there around the spleen to allow for the tumors that grow a little bit outside the organ. But anyway, we minimize segmentations outside the organ. And then inside the organ, we must locate each one of the tumors that are described in the reports. And how do we locate these tumors? We use something we call a Ball convolution to locate the most probable location for each tumor described in the reports. So what is this Ball convolution? It's a standard convolution, but the kernel of this convolution is not a learnable kernel. It's a fixed kernel, which is binary and has the shape of a ball. So if the tumor has 30 millimeters, as in this example, according to the reports, the kernel of this convolution is a ball, binary, with 30 millimeters of diameter. The convolution will move this ball inside the organ. And at each position, the ball is basically summing all the tumor probabilities inside it. So the maximum output of this convolution is the most probable location for a tumor of 30 millimeters. Then the ball convolution basically finds this most probable location. And inside this location, inside this most probable ball, we maximize, our loss function maximizes the tumor probabilities. And outside this location, the loss function minimizes the tumor probabilities because tumor segmentations outside this ball are probably false positives. However, we do not want to make our tumors balls. So the tumors can have many shapes. And what our loss function does is it allows the tumor to have any shape that fits inside this ball that has the diameter from the reports. with a little bit of margin as well. So inside this ball, what we do? We estimate from the reports how many voxels this tumor should have. Again, this is based on a volume estimation. So for example, here we estimate from this diameter that this tumor should have 14,000 voxels. Then inside this ball, which is the most probable location for the tumor, we find the 14,000 voxels with highest tumor probability. And our loss function further maximizes the probabilities in these 14,000 voxels. Then around this region, we have a tolerance margin where we do not penalize. So we do not make these probabilities there higher or smaller, again, because diameters are not perfect. And then after this region, after the tolerance margin, we minimize probabilities. What if the report says there are multiple tumors in this organ? Then we just do multiple ball convolutions. So we begin with the largest one, and we use a ball convolution to locate the largest tumor. Then we remove it from the segmentation output. We go to the next largest tumor, we find it, remove it, and then we repeat this process to locate each one of the tumors and optimize each one of them using this procedure that I described. Two questions that I commonly receive after presenting this loss that I will already answer is, what if the AI found no tumor? How can this loss work? That's a good question. But first thing is, what does finding a tumor mean? Even if the AI has a low, if the segmentation model segments the tumor with a low probability. So imagine that this red region here has 10% probability, but around it is 1% tumor probability. Even in this case, the ball convolution will find this location because this is the most probable location, and it will further boost the probabilities in this location. So even if the AI model finds a tumor with low probability, this loss works. What if the probabilities are all zero? Then it would not work. But this is extremely unlikely because we have the volume loss, and the volume loss has a very strong penalization when all probabilities are zero. So you must think that these two losses work together. The volume loss helps the ball loss. Another question that I sometimes get is, can't this ball loss enforce a false positive? So imagine that this AI, instead of finding the tumor here, which is the darker region, it finds a wrong tumor in the top of the spleen. Then it's possible that in this sample, the ball loss would enforce this false positive. But we must think about the entire training data set. If the ball loss could enforce a false positive in one sample. But then in the next sample, imagine that the patient has no spleen tumor. The spleen is healthy. If the AI still finds the same false positive, the loss function will penalize it. So overall, even if in one sample a false positive is emphasized by this loss, in the next sample it will be penalized. In the end, if you think about the entire data set, the only stable solution for this loss function, which will minimize the loss overall, the average loss around in the entire data set, the only solution is if the AI model is able to understand where the tumors are, which organs the tumor are, the diameter of each tumor, and how many tumors there are. In other words, the only way to minimize the ball loss over the entire data set is if the AI truly learns to segment the tumors. Okay, now our third loss function, which is the attenuation loss. So what is attenuation? Attenuation is simply, in simple terms, whether the tumors look dark or bright. Are the tumors darker or bright than the surrounding healthy organ tissue? So for example, here we have a hypoattenuating spleen tumor, meaning that this tumor is darker than the surrounding organ. It could also be a hyperattenuating tumor, meaning it would be brighter than the surrounding organ, or a isoattenuating tumor, meaning it's basically similar brightness to the organ around it. So the reports usually have the attenuation of the tumor, and we want to use this information to also improve our tumor segmentation. How to do it? Again, we will use the segmentation model to segment the tumor, and then we will use the outputs of this model, the tumor segmentation mask, to estimate what is the average AGU value of the tumor. AGU value is basically the brightness of a CT scan. So each voxel, each 3D pixel in a CT scan has a AGU value, which means how bright it is. So we use the tumor segmentation mask to calculate the average, the mean AGU value of the tumor, and we also calculate its standard deviation. And then we also calculate the average and standard deviation AGU value for the organ. To do this, we use again the pre-saved organ segmentation mask, excluding the tumor region. And then we estimate the organ average and standard deviation for its AGU value. So basically, we have four numbers here. The AGU value, mean and standard deviation AGU value for the tumor and for the organ. These four numbers go into a MLP, multi-layer perceptron, a very small network that acts as a classifier. The MLP will classify if the tumor, whether the tumor is hyperattenuating, hypoattenuating, or if the organ has mixed attenuation, meaning some tumors are bright, some tumors are dark, or isoattenuating tumors. So it's basically a classifier with three output neurons, hyper, hypo, and iso/mixed. And we train this classifier with a standard cross-entropy classification loss. And the label for this classifier is just the attenuation that we got from the reports. So how does this help the segmentation model? It helps the segmentation loss model because the gradients of this loss function is backpropagated first through the MLP, so it trains the MLP, and then it's also propagated through these calculations of mean and standard deviation to the masks, and then from these masks, which is the output of the segmentation model, the gradients is backpropagated through the segmenter. So in other words, the segmenter learns to segment tumors better to help the classifier, the MLP, classify them as hyper or hypoattenuating. For example, if the segmenter segmented a tumor here in the top of the spleen, it would be a bright region. It would not, the MLP would not be able to tell that this tumor is hypoattenuating. But if it segments the tumor correctly, then the MLP, which is a simple network, can easily tell, okay, this is a hypoattenuating tumor. Okay, so this is our methodology. Three loss functions to use reports to train tumor segmentation models. Now let's go to our results. I begin with some results on public data. So these results are fully reproducible. You can go to our GitHub here in the QR codes and train and reproduce these results exactly. Here I use it two data sets. The first one is PANTS. PANTS is currently the largest pancreatic tumor segmentation dataset. It has 1.1 thousand CT scans with pancreatic tumor masks. The second dataset is MERLIN. MERLIN has 25,000 CT scans and reports no mask, and 2,000 of them have pancreatic tumors and reports. So what this plot show you is if you train only with PANTS, only with CT scan and masks, standard segmentation, you get the results in gray. If you train with PANTS plus MERLIN, so you have CT scans and masks in PANTS and also CT scans and reports in MERLIN, and here you use our reports prevision methodology, then you get the results in orange. So we see an improvement of pancreatic tumor segmentation of 11% sensitivity, 10% specificity, and 10% F1 score in the MERLIN test sets. And then in the PANTS test sets, we still see a large improvement with up to 5% improvements in F1 score for detection of pancreatic tumors. So even with the largest public pancreatic tumor segmentation datasets, if you add reports to it and use our methodology, you have a lot of performance to gain. Here is another interesting result. Basically, the summary of these plots is that no matter if you have few tumor segmentation masks or if you have many tumor segmentation masks, if you add CT scans and reports and train for methodology, so you increase your dataset size with these pairs of CT scan and reports, you gain a lot of performance. So here, for example, we trained with 50 pancreatic tumor segmentation masks, and then we added 2,000 pancreatic tumor CT scans and reports. And this improved DICE by 11.1%. Here, we trained with 350 pancreatic tumor masks. And then when we added the 2,000 reports, we gained plus 8.4% DICE. Even here for kidney tumors, when we trained with almost 2,000 masks and then we added almost 3,000 reports, we gained 4.3% F1 score. So again, no matter if you have few or many masks, if you add reports, you still have a lot to gain in terms of performance. Another important result, here we compare our methodology, our super in orange, against many other methodologies. So here we have the NNU-NETs and segmentation. Both are basically standard segmentation models that train only with masks. Also, then we have other models genesis, which can train self-supervised with CT scans without mask, plus the masks. And then we have other methodologies that can learn from reports in some ways. So for example, multitask learning. Here we basically extract from the reports classification labels, meaning is there a tumor or not for each organ. And then we train for classification plus segmentation. So multitask learning for both segmentation and classification. We have report-guided pseudo-labels where we use AI to create pseudo-masks for the entire data set, and then we use reports to remove false positives, and then we train for these reports-guided pseudo-labels. And we have CLIP, where we pre-train with CT scans and reports using the CLIP loss, and then fine-tune with segmentation masks. So all of these methodologies, as you see in the plots, give results that are much lower than our report supervision. And the reason is that report supervision is more efficient in learning from the reports. And the reasons are summarized here in these plots. So first, report supervision can learn from CT scans without masks. It can learn from reports. It can learn from the detailed information in reports. So report supervision learns from the tumor, number of tumor in the reports, the size of each tumor, the location of each tumor, and the attenuation of each tumor, unlike most of these methodologies that do not use all of this information in training. Another very important thing, report supervision directly optimizes segmentation. So here, our losses, our new loss functions, they are only low when the segmentation is accurate. If the segmentation is not accurate, our losses are high. So reports are being used to directly improve segmentation. That's different, for example, from CLIP, where the reports are used to improve an auxiliary task. So CLIP is a task of matching. We have a set of reports, a set of CT scans, and you need to find the correct pairs. The AI finds the correct pairs. And we hope that by learning these auxiliary tasks, the segmentation will also improve. It does improve, but it's not a direct optimization. So it's possible to have a good CLIP loss, but still have a bad segmentation. But it's not possible to have a good report supervision loss, but a bad segmentation. A good report supervision loss needs a good segmentation. And finally, report supervision penalizes false positives and false negatives directly, unlike other methodologies. So if the segmentation does not find a tumor, the segmentation model does not find a tumor, it's penalized. If it finds tumors that do not exist, it's also penalized. Okay. So other interesting results, report supervision improves early detection. So here we analyzed performance on tumors smaller than 2 centimeters, so small tumors, and report supervisions gave us strong improvements, 20 plus 26% sensitivity, plus 15% F1 score, plus 8% DICE for pancreatic tumors. And that's in external validation and in comparison to training only with masks. External validation here, I mean that we trained in one hospital, UCSF, and tested in another hospital, in this case, Johns Hopkins Hospital. Okay, now I will explain the extension of this work. Most of what I talked about, the results I mentioned right now, were mostly in the MICCAI paper, and this is a large extension that we are preparing right now. So this is currently a preprint, and it's now a large collaborative work. And our objective here is to address the problem shown in these plots. The problem is that for many organs, we have no public segmentation mask. So how do we address this problem? We address this problem by creating a very large data set that covers all of these tumor types with reports. So we collected a total of more than 115,000 CT scans and reports, mostly from UCSF, but also from other sources like Stanford's. And to collect this data set, first we analyzed 30 years of radiology reports with LLMs to find the cases of interest. These were more than 500,000 reports. And then we found these 117,000 ones of interest, which are 98,000 reports with tumors and 18,000 normals. So we assembled this large data set. And the next step is we wanted to create some masks for this data set. Why? Because as you see here in this plot, when we have masks, we get better results. Even if you have many or few masks, if you add reports, you improve results, masks still are useful. They improve the performance. So our next step was creating masks. So we have a large team of radiologists helping us in this task. And we are doing a new active learning methodology based on the reports. So basically, we begin by training our super only with CT scans and reports. Then we use this AI model to create pseudo labels to create masks for the entire data sets. Then we compare these masks to the radiology reports. So basically, we create a report score, which shows how well the reports and the mask aligns. Basically, this score is based on our loss function. If the reports and if the mask has the correct number of tumors, the correct size of tumors, the score is high. Then from this score, we can select the worst masks, the worst pseudo labels, pseudo masks created by the model. We select these worst masks, and then our radiologists create manual masks for these cases. So they correct the AI-made masks, and this is much faster than creating masks from scratch, about 5 times faster according to our radiologists. And then we train again the segmentation model using these masks plus all the reports, and we repeat the loop. So again, we create masks for the entire data set, we find the worst ones, radiologists correct them, we train, and so on. So in this loop, we are improving the segmentation model. At the same time, we are annotating, creating masks for the data set. In the end, we have from 29 to 180 masks currently for each one of these 7 tumor types. In total, this is a large number, more than 1,500 masks. And as you see, those are tumor types that are not available in public segmentation data sets. You do not find masks for these tumor types, except adrenal, where you find like 50 masks. And there is no public segmentation model that can segment these tumors. So what these results here show you is if you train only with the segmentation masks, these 1,500 masks, you get the results in gray. Here is the average in the right bottom part. If you train only with the reports using no mask at all, you get the results in yellow, which are higher. So if you train with many reports, you can get a better segmentation model than if you train with few masks, which is pretty interesting for me. And then if you train with both masks and reports, you get the best results, which are the ones in orange. And interestingly, the performance of this AI model is already higher than radiologist performance reported in the literature for many of these tumor types. And the reason is that detecting these tumors in CT scans is very difficult. So, for example, for prostate tumors, they are very difficult to detect in CT. Normally, they are detected in MRI. But what we show here is even though it's very difficult for humans to detect these tumors, they have only 44% sensitivity in the literature. Our AI can detect it with 84% sensitivity. So this shows that AI can have the potential to allow in the future humans to detect these tumors in CT scans, making CT scan a tool for opportunistic detection. So the AI can tell the radiologist, say, there's probably a prostate tumor in the CT scan. And then the radiologist can ask for follow-up exams like MRI to confirm this finding. And another note, even the large report generation vision language models like Magema from Google cannot detect these tumors. We tested it, asking it to generate reports for the CT scans, and the sensitivity for these tumor types was below 2%. So basically, it could not find these tumors. Here are also the multi-tumor results, but for external validation. So here we trained in UCSF and tested on Merlin. So it's trained in one hospital, actually a set of hospitals, because the UCSF system receives data from multiple hospitals in California. And then we tested in the Stanford Hospital, which was never seen in the training data sets. And again, we see results similar to the last one. So we see here, for example, an improvement of 13% in sensitivity, 8% specificity, and 11% in F1 score when we include reports in training versus training only with masks. So finally, we go to our conclusions. Our main question in this work is, can reports improve tumor segmentation? And the answer is yes, they can improve a lot. You see double-digit improvements in sensitivity, specificity, F1 score, DICE. Even we can train and get stronger results with zero masks. And no matter if you have few and medium or many masks, if you add report to training, you see a big improvement in performance. Report supervision can improve performance for small tumors, are important for early detection, and for unseen hospital in external validation. We showed that training with many reports can give you better performance than training with few masks, which is interesting. And it's similar to what we see in other AI fields, like weak supervision at large scale can beat strong supervision in smaller scale. And most importantly, report supervision unlocks the segmentation of more tumor types. So by training with reports, we can segment tumor types for which no public segmentation mask exists, making a democratization of multi-tumor segmentation. We do not need to ask radiologists and spend millions and years to create masks to be able to segment these new tumor types. So we are going to release the first public AI to segment these 7 tumor types that are not in the public datasets nor segmented by public models. And we will also release image, CT scans, and masks for these tumor types. So that's it. Please feel free to visit our GitHub and Mr. Giovanni, our super, and scan our QR codes.
So thank you very much, Pedro, for the great presentation. Everyone can write your questions in the Q&A session. I see a couple of questions already written, so please write it down there. I just have one question, Pedro. Which LLM you use? And then I don't know if you have seen any hallucinations or any problem by using an LLM to extract the data, the metadata to get like a number of nodes, the centimeter, volumes, and so on to train the segmentation task.
That's a good question. So the LLM that we used originally is Llama 3, the large one, 70 billion parameters. And we had a manual evaluation. So we ran the LLM over, I think, 250 cases. And then we asked a radiologist to analyze the outputs. And we find the accuracy was above 90%. So it is a good accuracy. It's comparable to the accuracy of labelers in famous data sets like Checksperts,
Mhm.
but it's not perfect. So for training, we see that even if the accuracy of the LLM is not perfect, still we can get a lot of improvements. For testing, if you want to use the information from reports to test and calculate sensitivity, specificity, then we manually verify the outputs to ensure that your testing set is correct.
Okay, that's good. And then I will go through the questions. We have an anonymous question. Can you please clarify if the masks used for evaluation are created by the model and then adapted by clinicians?
The mask used for evaluation. Okay, so we were talking about the test set where we calculate dice. Okay, yeah, here we have dice for pancreas tumors, and this is evaluated in the JHH, Johns Hopkins Hospital data set. So this is the large data set that I mentioned at the beginning of my talk that took 5 years. So every one of these masks were manually done by radiologists over a large periods of time with a large cost.
That's, I think, clarify. Then Aurot asked if you were planning to extend this work to other imaging modalities such as MR or ultrasound.
That's a great question. Yes, I believe this work is directly applicable to MRI because it's very similar in structure to CT. Also, the reports are similar to CT. So I think this would work perfectly in MRI. And we do have a current collaboration to extend this to MRI and also to PET-CT.
Good. And then another question regarding the LLM. You mentioned that it was Llama 3. What was the prompt that you used to extract the data, the metadata, and then if the prompt was created by radiologist?
That's an excellent question. Yes. So the prompt creation was actually a complicated procedure. So we had many trial and errors. We tried one prompts and then radiologists analyzed the results and then give us suggestions. So we improved our prompts. So in the end, yes, we have a prompt that's quite complex and encodes a lot of radiologist knowledge. So it explains to the LLM what is a tumor, how to identify if there's a tumor or not. And all these prompts are available in our GitHub. So yeah, everything is available in the GitHub.
Do you have to update the prompt because I guess if you're using the data set with the report from the Johns Hopkins University, they are standardized following the specific manner to write a report. Uh, like probably in another university or another hospital, they write in a different manner, and I don't know if the prompt will work in the same way or not.
It does work. So this is one of the big advantages of LLMs. So someone already asked me why did not this work? Why was this not done earlier? And I think one of the reasons is the advent of LLMs. So in the past, it would be very difficult to extract all of this information from reports because reports can be very different between institutions and even between different radiologists in the same
Hmm.
institution. So we see that the LLM actually can work well with the same prompts over different institutions. For example, Stanford's, Johns Hopkins, and UCSF.
It's good. And then two questions from Nalan. Radiology sometimes makes tumors, especially small and subtle ones, that you show early, and the reports are based on the interpretation. So if we want to use those reports as guidance, how should we deal with the fact that the information might not be perfect?
That's also a very good question. And I agree. So if you want the AI to strongly surpass radiologists, we need ground truth that is above the radiologist. And what we are doing currently is we are also using the pathology reports to confirm these findings. So from the pathology reports, we can have strong information from biopsy about whether this patient truly has a tumor or not, and if the tumor is malignant or not. So now we are in this extension of this work, incorporating the pathology information also in training and testing.
And the second question is, how does the model compensate for segmentation errors from total segmentator, especially in challenging cases?
Sorry, what's the question?
So how does the model compensate for the segmentation errors from the total segmentator? So I think this is from
Ah,
the
for the
organs that you.
organ. Okay, I see. That's a good question. Yes, the organ segmentation masks are not perfect. I say they are good because usually organ segmentation models can reach 80, 90% dice, for example, as we see in the touchstone benchmark, but it's not perfect. What we do is we have some dilation of the mask to compensate for errors. So we do some binary dilation, which basically extends the organ between 1 and 2 centimeters. This can compensate for some errors. It gives you a margin of tolerance, and it also compensates for tumors that grow beyond the organ, which is also important.
It's an important one. And then how can we improve the dice score during tumor segmentation for 3D CT scans?
How to improve the dice score for tumor segmentation in 3D CT scans? Mm, If I get the question correctly, yes, we see that training with radiology reports improves the DICE score. So here we have the evaluation of DICE score for pancreatic tumors. As I say, we have this very good ground truth here, the masks. And when we add the reports to training, we have an improvement, a strong improvements in DICE score.
So yeah, it improves. And then I will
Yes.
answer the last question, which is the recording of this will be available. It will be it's in the YouTube channel of the MICCAI Society. You have a playlist with all the previous journal club sessions. So if you have missed this talk or you want to watch it again, you can go to the YouTube channel. So I think that was it from the questions. Thank you so much, Pedro, for the presentation. It was very good and nice, really, really good work. And yeah,
Well,
congratulations on the best paper award.
thank you. Thank you very much. Thank you for the invitation. It was great to present this work here.
So let's see you in the next MICCAI.
Yes.
Have a have a nice weekend. Bye bye.
Thank you. Bye.